Thanks to the scientific committee for inviting me. And I will be talking about something contained in several articles and preprints. You can see the co-authors, I think some 10% of this conference is involved in this topic. Okay, so let me start with some general definition. So consider a norm on L infinity. It is not a real norm, it can attain infinity, right? It's something like extended norm. So for such a function, you can define fin of this norm. So those are just the sequence for which the norm is finite. So in this way, you can define L infinity, L1, L2, and so on. You can also define exhaustivity of this norm. And so here you take all the sequences whose tails are convergent to 0 in norm. And if you, in fact, you can define this exhaustivity in another way, more classical for Banach space theory. You take a norm C00, so sequences of finite support, and you complete this thing according to with respect to the norm. And in this way, you can define C0, also L1, L2. So this is the language of analytic PIDs, right? You could see it on Jordi's talk. So it is not very usual to use it for Banach spaces, but I found it convenient because, first of all, I'm more set theorist. Secondly, this language reveals some symmetries between the theory of analytic PIDs and okay. So if you take norm which is nice enough, I didn't want to write down what does it mean nice. There are some technical but natural conditions like lower semi-continuity, monotonicity. Then those sets equipped with this norm are Banach spaces. And in fact, I haven't written this down, but this exhaustivity is a Banach space with unconditional basis. And we have such a theorem that, in fact, every Banach space with unconditional basis can be seen of this form. So referring to the symmetry between theory of analytic PIDs and Banach spaces, this is like Solecki theorem, right, for analytic PIDs. Solecki's theorem tells you that all analytic PIDs can be represented as exhaustivity of some submeasure. So here we have the analog for Banach spaces. Sorry, I don't... Yeah, but this basis is this condition. It is enough. This unconditional basis. Yeah. So of course. For this talk, yes. And unconditional basis, yeah, meaning countable basis, yeah. Okay. Another theorem. I'm not going really to use it on this talk, but I want to present it. This exhaustivity does not contain a copy of C0 if and only if those two spaces. So this is the analog of Mazur's theorem from analytic PIDL theory. So you can think that analytic PIDs are just discrete versions of Banach spaces with unconditional basis, or Banach spaces with unconditional basis are linearized versions of analytic PIDs. One more thing, which is not really connected to something, I think, with something from theory of analytic PIDs. If your space does not contain a copy of L1, then we also know what is this space fin. It is double doer of exhaustivity. Okay, but today I want to concentrate on very particular norms induced by families of finite subsets of natural numbers. So you fix a family of finite subsets of natural numbers. Hereditary, meaning if you have something in your family and you take a subset, then you also have it in your family. And also, I would like it to cover whole space of whole set of natural numbers, okay, to avoid some trivialities. So for every family like that, you can define this kind of norm. So here you just, so somehow the family tells you where you can sum up, right? And then you take supreme. So some trivial examples. So for example, if you take the smallest possible hereditary. Sorry? Yes. And but then we go to the sphin spaces and then yeah. But this norm is again extended norm if you consider it in infinity, right? So if you take the singletons, then you obtain just the supremum norm, right? Because you are not allowed to sum up anything. So it's just the supremum. So here you will get an infinity and C0. To the contrary, if you take the biggest possible family, you take every finite set, then you can sum up along everything. So you get L1 norm. So you have L1 here and L1 here. And the convention, I will not to write this exhaustivity all the time. By XF, I will denote this space, and I will call such kind of spaces combinatorial Banach spaces. Okay? These are for me combinatorial Banach spaces. Okay. So coming to the non-trivial examples, the most canonical one is the Schreier. It appeared already at Niels' talk. So Schreier family is that, right? It's family of sets bounded by, or cardinality is bounded by the minimum. And this guy is called the Schreier space. What is important, this family is compact. This is a family of subset of natural numbers, so it is a subset of Cantor sets. You can consider Cantor topology. For hereditary families, in fact, compactness is very easy. It has this combinatorial explanation here. It exactly means that there is no infinite set whose every finite subset is infinite. And by this, you can easily see that Schreier's family is compact. So this kind of spaces for compact families are well studied. Even in this room, there are many people who are really specialists in this topic. For compact families, these combinatorial spaces can be embedded into space of continuous functions on F, and then by Pouchinski theorem, you know that they are C0 saturated, meaning every subspace, non-trivial subspace, has a copy of C0. So also all these combinatorial spaces for compact families are C0 saturated. And one more remark. So this is just a general remark. So you can define other compact families like higher order Schreier families and lunatic sets or many other. And you have nice tool to analyze it. You have, for example, Cantor-Bendixson derivative, since these guys are these compact spaces are compact sets are scattered, right? Countable and compact. But what I'm interested in is not this case. I mean, I'm interested in the situation when you take non-compact family. And there were not so many examples, and it is a kind of mystery for me why it is like that. There are not so many examples in the literature of data spaces for families which are non-compact. So if you take non-compact family, then immediately you have copy of L1 inside. Actually, one example already appeared, right? If you take all the finite subsets and then you get L1. So of course, those spaces will contain L1s. And one of the most natural and important examples, and I will come back to it several times during my talk, is the following. So what you do, you change your structure a little bit. So instead of natural numbers, I want to look at dyadic trees. So coordinates are here, they are the nodes. And so of course, this is countable, right? So it doesn't really matter if you take natural numbers of this guy. You can enumerate it if you want. And using this tree structure, you can define very natural hereditary families, many finite anti-chains and finite chains. And you have these families, you define the norm, and you have the combinatorial space induced by this norm. So, okay, let's take this anti-chain space. We'll call it XA. So how does it look like? So look, on the anti-chains, even the infinite ones, we are allowed to sum everything. So there is a copy of L1 there. But on the branches, you have copy of C0 because you are not allowed to sum anything. I will come back to these spaces because they are important, but now maybe I will present something more particular. So the following family. So what you do here? Here you fix an interval partition, and you are allowed to take to your family all the guys such that here you can take everything, but from this guy you can take only half, from this only 1/3, and so on and so on. And in this way you produce a family. We call it Farag family because it was motivated by some example of analytic p-ideal defined by Farag. So this is this instance when so I'm doing something opposite to Jordi. Right? Jordi wanted to use structures from Banach spaces for ideals, and I'm doing the opposite right here. And what is the, so you have a family, so you have the norm, so you have this combinatorial space. What it is, not something very special. It is not isomorphic to L1, but it is L1 saturated. So again, every subspace, non-trivial subspace contains L1. In fact, it has the Schur property. And in general, let me remind you that we have this following chains of implications. So Schur property implies L1 saturation, and L1 saturation obviously implies no copies of C0. So for some time, there was an open question, can you reverse this implication? And okay, so it was an open problem if L1 saturation implies Schur property. It was answered by Bourgain. So he presented some example, and then there were more examples. In fact, there are now, I think there are many of them. They are quite involved. So using this machinery, we can produce another example. And maybe I don't want you to read it. I mean, it's not necessary to read it. It's very difficult, but needed for now. This is a family. It is a variation on this Farag's family. Or less the same thing, but we did something to this Farag's family and we obtain this kind of thing. And this is another example. And to prove it, it's maybe not so easy. To show that there is no Schur property, it's easy. To show that it is L1 saturated, you have to calculate something. Nothing is for free. But the important thing is that even if there is some difficulty, it is not in the definition of the space. Right? The space is very easy. If you compile this definition, it's really very easy. So I think this is one of the easiest examples, this kind of spaces. So this is how you can profit from the theory of analytic p-ideals, from the examples from the theory of analytic p-ideals. Okay, so now back to this dyadic trees. So after for some time we were doing we were producing examples with Barnabas of this kind of spaces, and we were sure that they are very simple in the sense that they are just alloys of C0 and L1s. And we had even conjecture that if you take combinatorial space, then if you take a subspace, then for sure you will get C0 or L1 inside. So, and we were very, very wrong, as was pointed to us by Kevin Binland. In fact, this space, this space defined by anti-chains, it turned out that it is well-known space in the Banach space theory. Just the description was different by Martingale. It is stopping time space. It was defined by Rosenthal, and he proved that every LP is inside. And what is and by the way, why we defined it? Why we defined this family? It was also inspiration from the analytic P ideals, because this is motivated by so-called trace of null ideal. So somehow this trace of null ideal gave us something which was already well known. What was even more striking for us, this space defined by chains is even universal for Banach spaces with unconditional basis. Which is, if you look a little bit on this space defined by chains, you can see that there is some strange analogy to the space of continuous functions on the Cantor set. So maybe this is not very surprising, but after you think, so what does it mean? That these combinatorial spaces can be very easy on the surface, but inside you can have very difficult things, very complex things. The problem with the spaces is that it's very difficult to see how, for example, L2 lies inside. Anya is able to do that, to see that, but I'm not. So the next example I want to present is an example actually also invented by Anya of a combinatorial space when you can really see the copy of L2, let's say, or any other Banach space with unconditional basis, in fact. Okay, so what you do, you again play with this Farah. You have still the same partition, but now what you take to your family, you take all these guys such that if you look at the sequence of proportions of the ratios, it belongs to the ball or on the dual space of your chosen space, for example, L2. Okay, and then what you do, you take vectors which look like that. These are vectors of norm 1, right? These are vectors of norm 1 in this space. And they generate isomorphic copy of Y. And it generates, what is more, this copy is complemented. And the reason is not so difficult. It's just because the norm is induced by the elements of the dual space. So you have a combinatorial object family, but you can encode geometry in this object, in these combinatorics. Okay, we have more examples, and in fact, you know, there are many families of finite sets, many interesting families. So you can use different structures, analytic, algebraic structure, measure theoretic structure to define some families. And then having family, you have norm, and having norm, you have combinatorial space. My hope was that if you take something beautiful enough, so the family which is beautiful enough, somehow this beauty will lift up to this Banach space. Okay? So if you take something generic, then you will get also something generic on the level of the Banach space. Sometimes it's not true, sometimes it's true. So, for example, what can you do? It's for example, you can think about universals family of finite. What does it mean? It means that whenever you take a family of finite sets and some finite subset, you can find in this universal family exactly this piece of this family G, right? So this is a natural concept of universality for this spaces, and you can do that. I mean, it exists. This is classical. You can take phrase limit of families, and in fact, this is random hypergraph or random hereditary hypergraph, something like that. Yes. Sorry, if I haven't put that, of course, every family here is hereditary for me. No, it's I mean something more that maybe okay. Yes, maybe I should have. So I take what I take all the intersections of the family of the elements of the family G with N. Right? So like trace of the family. Sorry. So maybe I should. Maybe I screwed something up here. Okay. Okay. Sorry. Yes. Because when you okay. Yes. Because to produce this family, you need something. So I'm sorry. I confused it. To produce this family, you need to consider. So this is just the random hypergraph. Okay. So very generic structure. And it is no surprise that if you take the Banach space induced by that, it is also universal. And for Banach spaces with unconditional basis, in a special way, in a complemented way, that every Banach space with unconditional basis sits in a complemented way in this space. So this is there is a space with this property, so-called Pełczyński space, and in fact, Pełczyński proved that every space with this property is isomorphic to his space. So this is just the Pełczyński space, right? What we obtained. But Pełczyński asked, is it true that if something stronger is true, does every Pełczyński space is even more close to each other? I mean, if the base of one space can be permuted in the way to obtain another one. And our Pełczyński is not like that. Okay, so we obtained some Pełczyński space, but which is of a different sort, okay, by using this machinery. Okay, so of course you can produce, as I said, you can produce many examples. Just take your favorite family, plug it in, and see what happens. And at some point you feel you have too many of these creatures, right? You would like to have some structural theorems. You would like to prove some general things. And with that, it's much more difficult. So one of the theorems, I already mentioned it, one of the theorems I mean is like that. So this combinatorial space does not have a copy of L1 if and only if the family is compact. So you have a combinatorial condition on the family and the geometric condition on the Banach space of characterization. So it is natural to ask, what about not containing a copy of C0, right? How to characterize families in a combinatorial way, which gives you something, which does not have a copy of C0. And at some point we had a game with Barnabas. I was proposing conjectures, so I thought maybe perfect in the Cantor set, in the Cantor way, families, or perfect in an Lentac way, or something like that. And Barnabas was answering with Cantor examples. And he won, so we have nothing. There is no. So it can mean, maybe it means that there is no combinatorial characterization of this property. Yes, of course, there is this. Yeah, but of course. No, I mean we tried, of course. We tried different things, and you can ask this kind of questions for other properties like Schur property, L1 saturation, whatever, and usually it's difficult. So maybe some properties are more geometrical, some properties are more combinatorial. But I want to present a successful attempt for characterization theorem. And again, I want to come back to this chain-anti-chain. So Bank and Odell proved that these two spaces defined by chains and anti-chains are connected to each other with a very strange way. Namely, if you take this exhaustivity space for chains and you take the dual, you would attain the fin of the anti-chain space and vice versa. So they are somehow dual to each other in some sense. So, okay, we will call this kind of pairs geometrically dual. And the question is, can you characterize it? I mean, the first question is, can you find another interesting examples of these pairs? And the next question is, can you characterize it? So can you characterize geometrically dual families? Okay, so how to do that, or how to try to do that? So first of all, there is this concept of transversal to the family. You have a family, you can consider an orthogonal or transversal family. It's the family of all sets whose intersections are at most one with everybody from your family. And we say that two families are combinatorially dual if they are in this relation, so one is transversal to another. And it is not hard to see that this is the necessary condition. So if you want to have two geometrically dual families, they have to be combinatorially dual. Okay, so so in fact, I'm talking about pairs of families, but I can talk about just one family, yeah, because the other one is just a transversal of the first one. And what we are looking for, if we are looking for combinatorially dual families, we are looking for guys who have this condition. So if you take transversal of the transversal, you get what you had at the beginning. I will call it conformal. So maybe some examples. So if you take singletons, transversal, it's not very difficult to have at most one point intersection with a singleton, so you get all the finite sets. If you proceed, you will come back to the singletons, right? If you take anti-chains, what is the transversal family? Exactly the chains, right? Because these guys have at most one point intersection with anti-chains. And again, taking transversal to chains, you come back to anti-chains. And if, for example, if you take Schreier family, it's not like that. Transversal is the family of singletons, and you don't come back to Schreier family, obviously. Okay, so this is the remark. So if we have, this is in fact equivalence, right? Instead of speaking about combinatorially dual families, we can speak about conformal families. So what are these conformal? Yeah, they are both conformal. Yes. They are both conformal. So if you think a little bit, what does it mean to be conformal? You will discover that it means that to check that something is not in your family, it's enough to look at some two elements of this set. Okay, so to check that something is not an anti-chain, you just need to find two comparable elements and so on. And if you think a little bit more, you will discover that in fact these conformal families are exactly families induced by graphs in the following way. So here by graph, I mean graph whose vertices are enumerated by natural numbers. You have edges between some pairs of natural numbers. And if you take the family of all the cliques of this graph, it is hereditary family. Clique, you know, it's the set of vertices such that you have edge between each two guys from this. This is clique. And then the transversal of this family is the family of anti-cliques, so the sets where there are no edges. So what we are looking for? We are looking for families induced by graphs in the following sense. And the question, is it enough? So does every combinatorial dual pair of space is geometrically dual? So does every space induced by graph in the following way is combinatorially dual? We believed in that, but then Barnabas noticed that to have this geometric duality, we need, for example, that the extreme points of our space has to be a very special form. It can attain only 1 or -1 on its support. Even if we take finitely dimensional subspace. And it follows from the fact that although usually extreme points of combinatorial spaces are very wide and it's difficult to analyze, the extreme points of the dual spaces to combinatorial spaces are very easy, exactly of this form. At least they satisfy this condition. Okay, so noticing that, we notice that if in our graph we found such a piece, so this is called 5-hole. Hole meaning this is cycle, but then it's irreducible. There are no edges other than this. Okay? So this is 5-hole, 5 vertices. So if you have something like that in your graph, then remember, these vertices refer to natural numbers, so we can produce a vector. So we can produce this kind of a vector, just 1/2 everywhere. Notice that this is of norm 1, right? Because what we are doing, let me recall, we are summing along cliques, but the cliques here are only 2 points. So this is of norm 1, so this is on the sphere. And notice that this is an extreme point, which contradicts what we need from this fact. Why? Because if it is not an extreme point, that would mean that we can add something, some vector, and then subtract and stay in the ball. But if we want to add something, so it means we have to add something somewhere, but then to stay in the ball, we have to subtract it. But then to stay in the ball, we have to add it. And here we have a problem, right? We fell out of the ball. So the fact that there are odd many vertices is important. So if we have odd hole, then in our graph, it doesn't generate something geometrically dual. And the same applied to so-called anti-holes. So what is anti-hole? It's an anti-hole. I mean, this is a complement of a hole. So you erase all these edges and you add all which were not present. By the way, 5 anti-hole is the same as 5 hole, but 7 anti-hole is not the same thing as 7 hole. So if we want to have geometric duality, we have to think about the graph, but we have to avoid odd holes and odd antiholes. And this remark draws our attention to something called perfect graphs. So perfect graph, now think about finite graphs. Perfect graph is a graph where the chromatic number equals to the clique number. So here I put the definition. Chromatic number is a well-known concept, right? It's the minimal size of colors, which can be used to properly color graph. And clique number is the maximum size of the clique. So chromatic number cannot be smaller than clique number. It's very easy. So perfect graph is a graph with the smallest possible chromatic number. And it can be lived up to the infinite case. So an infinite graph is perfect if each subgraph, finite subgraph is perfect. By subgraph, I mean you erase some vertices, but you keep all the edges between vertices which stay with us, right? So it's called vertex-generated finite subgraph. Okay, so there was something like perfect graph conjecture asked by Berg, and that was the question: is every complement of a perfect graph perfect? It was solved by Lovász, and surprisingly, proving this theorem, he proved also exactly what we needed to know that geometric duality holds. Quite interesting. I mean, the formulation of this conjecture is purely graph theoretical, but in the proof, you have to consider, I mean, Lovász considered polytopes in finite dimensional spaces, extreme points of these polytopes, and that was exactly what we needed. So the corollary from the proof is that if we have perfect graph, it induces family and then families which are geometrically dual. So this is implication only in one side, but fortunately there was something like strong perfect graph conjecture. And I think for some time it was one of the most important questions, at least in graph theory. So this conjecture says that graph is perfect if and only if it does not contain odd or odd holes or odd anti-holes. Here odd means something bigger than 3, because for 3 the situation is different. 3 hole is a clique. And fortunately, some people proved that it is true in 2006. And you can use it as a corollary, because we already know that if something contains these strange holes or anti-holes, then it cannot give us anything geometrically dual. So by this, we know that if something is not perfect graph, then it has to contain these white things, and then it cannot. We don't have geometric duality, so we have full characterization, right, of geometric duality. Okay, and the last thing, I mean, it's more like an open question, or I don't know, or just to show you how it works. We have this characterization. It drew our attention to families. Actually, Jordi drew our attention to these families generated by colorings or graphs, the same thing here. And so, again, we have a lot of graphs, interesting graphs, so we can generate cliques and then see what are the Banach spaces. So from the point of view of set theorists, this is particularly interesting. So you fix a bijection between natural numbers and rationals. Then you export or import the inequality. the order. And you can define Sierpinski graph. This is something, R is an edge of a Sierpinski graph if there's two orderings, namely the natural ordering on the naturals and this imported ordering agrees. Okay? And so you have, in fact, you have many Sierpinski graphs. For different f's, you get something non-isomorphic. So the question is a sample question. So now what about this Banach space? So you generate cliques, you generate norm, you generate Banach space. And this is my belief that since Sierpinski colorings are important, very interesting from the point of view of Ramsey theory, the resulting Banach space also should be interesting, but we still don't know what it is exactly. Yes, it's perfect. Yes. So that was why we thought about it. Yeah? For some time, we even thought that if you take dual, it is isomorphic to the space, but I mean, it's totally not true. I mean, the dual is also Sierpinski graph, but for different functions. Okay, I think I'm done.